Okay, I'll go and log into MetaEdit Plus. I have here a number of repositories. I go to LWC repository. I have basically empty MetaEdit now. I'm just starting to create the models. And let's add here a new model. I have two different kind of languages. I have the piping language, piping and instrumentation diagram, and then I have other language for describing heating application. And what I have here is application for my home. The problem I have is that I have a cold water in the kitchen and hot water, but the kitchen is pretty far from the heating unit. So it takes quite a long time before the hot water arrives to the kitchen because it cools down in the pipe. Pipe is long. So what I would like to do is actually I would like to add a booster, a bump, which gives me faster the hot water. That's a sample here. And we also do the behavior here. So the city is providing me water, and obviously I also have then some kind of boiler. And within this system, I have two different kind of valves. This is now the British system. I have a separate cold, manual, maybe ball needle, and another one for the hot water as well, manual as well. And then I want to connect these. So here in the top toolbar, you can see the DSL, you can see the domain concepts. So I would say that the city water that I get goes to the boiler, and then it of course goes to also this ventil. And I'm using here possibility to connect multiple things at the same time rather than making one-to-one kind of connections. So therefore, if I need to enter information, what is the pipe? I only need to enter it once and not for each line separately. So this pipe is maybe the long one, maybe 5 meters. It's not covered. It's something like this, and then I have the normal short pipes too. And I would like to have here now this extra booster bump, which is just a normal pump, and this pump is then connected to my boiler. But then I also need to say how this, and by the way, this should be, because it's hot water, it should be somehow thermally insulated so it doesn't lose the heat. And to know that how the, when I need to have the booster, I also have here a flow sensor. So I call it flow 1. It's a flow sensor, and it is controlling, and it's also out of sight. I can't see it. So therefore, the notation changes as it is in the specification of LWC task. But because this is piping and instrumentation languages maybe made sometime 70s, people didn't have colors then, I a little bit adjusted it so that the model becomes easy to read and follow that what kind of sensors I have here. And then I can do the connections. So this is again the long line, and of course I want to have a thermally insulated there that I don't lose the heat. So something like this. And of course I could also have in my case, I have a remote heat system. So the city provides me just hot water basically. And I use the hot water to connect my heater to my boiler. Something like this. And I could continue and design it as you see. So you get the feeling what it looked like. But then I also would like to do a controller for this pump. So I'll create a new diagram for describing the extra pump system. And this gives me the state machine, so I can connect things here. Okay, I start, I initiate the pump, And then what I would like to do is I would like to start controlling the pump. And the ways how I can write things here, I can write things just like I want. I don't need to write in like I do programming, because we really need to raise the abstraction to the domain level as well. The code generator then translates the names which I give here as they should be. And then I can connect things. And of course, I have the rules here that if I want to do illegal things, it will check them. Similarly, it will check also illegal things here. So for instance, in the LWC Metamodel, I can only have pump which has one outgoing port. I can only send from pump flow or liquid to one place. So if I want to make another connection to somewhere else, it knows that I'm breaking these domain rules. Don't make such a piping layout or piping design. And then I can reuse some of the things here from the domain concepts directly. So what I do here in this behavior design is that I can reuse the same concepts that I have here in the instrumentation world. So I could make a design which says that, well, if my flow detector, and I would also maybe put the graphics here on as well. So if it happens so that the flow is detected, so the normal pressure that city is providing me is working, so there seems to be some activity, then let's put then the pump boosted. So now we have the pump running. So I'm operating with the domain concepts like this way. And these DSLs are connected. So if I, for example, decide to say that I have a new kind of a pump, I have a Venturi pump which needs to have some extra incoming pressure, for instance, to make it working, then I have a new kind of connections available. So if I have a pressure somewhere here, and then I connect things, now I can connect things to here, to this Venturi pump port. And now I notice that my designs are a little bit wrong. Actually, I would like to give the hot water this way. Pipes don't have a direction. You just say how, with pumps, how the things are moving. So this is about what the language looks like, but I also implemented the complete language for the home automation system. So here you can see the same assignment that was given in the designs. So if I look some of the aspects here, like the pump, for instance, you can see the same kind of state machine structure, but now the condition is looked if the burner flame has been detected, then puts the pump on or off. There are more complex state machines, like for boiler, for instance. And here you can see that when the system is starting and there's a condition that has a condition that if boiler is warmed up or radiator is warm up, they need to be warm up, then let's control burner. And the same condition is used with negation here, not. And so if boiler B1 is not warm up or radiator is not warm up, then go to the wait for heat request state. I also implemented here exit and entry because they were somehow proposed by the reference implementation. But as you can see, we, for example, don't need to use entry and exit. We could also make the actions here to this transition instead. So once the system has been designed, then you can, of course, the Metamodel has been checked there behind, so I can only make legal kind of things. And there are also separate checkers that if I want to do illegal kind of things or leave things unconnected, like sensor need to have actually multiple connections or valve need to have multiple connections, it will warn about those. And now when I have done this design, I can run a number of generators. One of them is an installation code generator, which is handy for the automation systems, so someone who goes to your home, he knows what kind of PC should be installed, and also this generator counts that how much pipe he must carry with him when doing the work. So it basically calculates the information from the model to see. There are also other generators mentioned in the task, sensor interface API, so it will show how basically the sensors in this case can be accessed outside by using some imaginary API. Also for those who prefer text, you can show the same model in text, and then this text is so much easier to, of course, read and follow. And you can also edit here from the text, so if you see something that needs to be changed, so this shouldn't be thermally insulated, you open it here and then you can go and modify the models. So this is just a presentation for the same description. And you can also run then other kind of code generators, like there are predefined code generators for model checking, metrics, Word documentation. And I'm running here ready Word document code generation that uses the template of the Word to produce the output. And then I have basically the ready document here with the stuff I had in the model. But the last piece, of course, is that we want that this runs somehow. So I have here a code generator that produces the exp files, which is the PLC code. But I also have here, TwinCat, which is auto-build code generator. So what this makes is that it produces me the TwinCat code, and TwinCat is the tool by Beckhoff that allows you to run PLC capabilities in a PC. So this is the environment where the code is now being generated. So what I have here is the base blocks, so which every heating system basically has, and then the type of code that is being generated is, of course, the whole program and all the state machine code that came out from these state models that you saw. So this piece of code that you see here is now being generated. And you may wonder why this code looks like this. I don't know. Reference code look like this. So someone was happy with this kind of code, so we tried to generate exactly the same code they had written today. And there are also data types being generated because they are also required by TwinCat. And but the thing I haven't generated here yet is the resources, because in order to run the resources, TwinCat need to have the system controller running, and then it configures it, and after that it can be executed. So basically, the same information I need to show now with the video, because TwinCat runs simulator only in a 32-bit machines, and I was then recording this with my XP machine. So what I have here is the framework. So I have the TwinCat with all the base blocks, just the commonality part. And the data types are empty. This just proves the case, basically. And now this is the platform that I'm generating the code. So here you can see there's nothing now. I press the TwinCat, then you have a lot of stuff here. TwinCat opens, imports the stuff into the TwinCat, runs the build, and finds 0 errors and 32 warnings. And once I then start the PLC, here it shows again the code being generated, the simulation, and the state machine code. But what TwinCat requires next, that in order to run this simulation, is that you need to assign and run the PLC system manager first and give the project file for it. And once you have given that, the next thing you can do is you can compile it, and then you don't have any warnings anymore. So I'll go a little bit faster here. So I'm opening here the twin cut. Yep. And then once you have opened the system manager, you have built the code, there's no warning, no errors, no warnings. The next thing you need to do is you need to say for simulation purposes how the variables from generated code maps to the simulation code in order to run the simulator. And I'm doing this here manually, and it would be very nice to generate that as well. But I didn't want to investigate how you do this mapping. So basically all the inputs must match to outputs, and then you can generate the mappings. And then you can run the TwinCat controller, and after that you can then go back to this PLC program, and it produces you these mappings then, and then you can load the application to the PLC and run it. So if you run it here, then things start to work again. So let's look then how this was built. What you see so far is a ready DSL user. So you could give this for piping and instrument expert, and he could use the familiar concepts and generate the code and do the work. But I'm using here the Workbench version, which has also access to the Metamodel. So I have here different kind of browsers to see my models and browse them. But I also have a browser called Metamodel. So I can see my two languages here, the piping and instrumentation language and the heating application language. So now at the same time I'm using these models, I can also modify the Metamodels on the fly. And all the models update to these Metamodel changes. Also, if we would be using in a multi-user environment, we would be a whole Beckhoff company making these systems. Someone could be changing the Metamodel when you are modeling. And you don't need to remember to download which DSL version actually I should have used. Just happens and works. So here you see the definitions of these two languages. Here's the piping language. It says each system has a name. It must be a string. It must be unique, which means that I can't build two piping and instrumentation designs with the same name. So they always have a different name. And there are also a number of other properties here. I can see here also the objects that I have. So for instance, I have the pipe relationship that I was drawing a connection. I have all the different kind of objects, and I have 3 different kind of roles. So if you look, for example, the pump object, the pump has a name and a description. And then the burner has just an instrument name. And I can add here new properties as I like. All these elements has also some kind of visualization. So here you can see the visualization given for the burner. And there's a name given here, but here's the symbol for the burner. And you can see here maybe also these connection points, that they must be somehow, like Paul was mentioning, they are closed circles. So you need to be able to define that things that are coming here shouldn't be mixed with the other stuff inside there. And here you can define how things can be connected and what kind of ports they have. You can also give different kind of conditions here for these things, and give the notation as you like it look like. But I try to follow what is given in the specification, and then I try to make it a little bit more user-friendly and easier to read. You can also give icons here. By default, you will get default icons, but if you want, you can also make your own if you don't want to use the default ones. The same is for dialogues. If for some reason you don't want to use the basic layout things, you can modify the layout of the dialogues as well. You also have different kind of rules on how things can be connected. And for instance, most typical connection in the piping and instrumentation language is that you can have pretty much connect everything to each other. But then you have also specific kind of connections there, like you have these heat ports for the radiator heat exchangers. And you also have a special connection for pumps. So there's a pump, how to put thing into the pump and how to take it out. The same kind of things you also have for state machines. So here you can see the heating application Metamodel, and you can see the bindings, like we can have a binding from start to state. These, by the way, you can also describe graphically, so you can make a graphical presentation of the Metamodel as well, but not the notation or generators or dialogues or things like that. Then there's also possibility to specify model linking. If you saw, I took a pump and I said, let's go to pump controller. So here is a definition of that each pump can be described in more detail in a heat controller language. So I'm combining and I'm a hierarchy of the models then. I also added, by the way, the same thing for state machines, that each state can have another substate machine, but that seems not to be needed in this case. And then I have a number of constraints, because the domain have rules, and you really need to express the rules, that people are not making illegal designs. So all the rules are here expressed in data. So implementing the piping and instrumentation language was something like a two-hour effort, because I don't need to program these rules, like let's say the pump, for instance. Pump can have only one pipe out role. So these are all data, and therefore if you change the Metamodel, you change the rules, you can also, MetaEdit takes care that the models also update them. The last piece is that I made the generators. So here you can see the generator editor. You can see the different kind of sensor interface generators, and most important was the generating the code for the twin cut. And here you can see that when I was pressing this magic button here in the toolbar of the modeler, I was pressing this twin cut button. So what this button basically makes, it calls twin cut auto build code generator. And this twin cut auto build code generator again calls EXP files, and it has own generator for main function block, and I can basically see how the function block basic states are being generated. And while I'm doing these generators, I may want to also debug them. So I would like to see how it looks like. So now actually you can see how the code generator works. So I run the main code generator. Let's go into a function block generator. Now it produces me files. So here you can see the current generator being executed. Here the models and model elements being accessed while generating. At the bottom I can see the type of code to be currently produced out. And if I have multiple outputs, so I can generate multiple files at the same time, then you can see them as well here. So you can see the piece of code being generated, and this is just the guidance for TwinCut, how to import the code into TwinCut correctly. But if we go forward, you will actually start to see how the code has been produced. And then you can run a bit faster to go, let's say, to more interesting places. Here we go now to the state machines. Now it generates the state machines for each of these. So you can see basically how the substate machines and starts to generate information from all the states that the underlying state machines have for this heat controller. So, and one thing why this is debugging is interesting is that while you are generating the code, you may wonder, what this is, where it is coming from. Basically, any of this information that you can see here underlined, you can trace back and see, oh, it's coming from here. So your model and your generated code is synced, so it makes your DSL development faster. I think I pretty much covered everything. I hope that I wasn't too fast on certain issues, but basically we implemented the sample system, we looked the implementation of LWC, and we looked the Metamodel and generator developed in MetaEdit Plus. And as you see, MetaEdit is pretty easy tool to use, and you can at least do demos very quickly. Thanks.